All right, I had some students asked to go over some problems here for the practice 5.1D, and I've decided I'll go over 1, 2, 5, 7, and 10. So I'm talking about the worksheet practice 5.1D potential difference here, and let's jump in. Number 1. A point charge of magnitude 5 microcoulombs is moved between 2 points, x and y. Point x is at a potential of 2 volts, and point y is at a potential of 8 volts. All right, so it kind of stands to reason that if you had some sort of a, let's see how I can show this, maybe a ball on a ramp, right? If you had some kind of a ball on a ramp, what would determine how much energy the ball would gain as it rolled down the ramp is not the height of either side, but rather the difference in the two heights, right? So if the height of both sides was high, then the ball would not gain much energy at all rolling across the ramp. It's where you have a high potential energy on one side and a low potential energy on the other. That's where the ball gains the most energy rolling down the ramp. Well, this certainly relates to what we're talking about here. Instead of potential energy, we're talking about electrical potential. So if we have a high electrical potential and a low electrical potential, there's a large potential difference between these two values. And that's going to indicate that we're going to gain a lot of energy or do a lot of work. Those two are the same between those 2 points. All right, so let's talk about number 1 here. Well, we say that the gain in potential energy, I'll just write right on here. The gain of potential energy, that is our change in energy, right? And we know that the change in energy is equal to the work. So we have this first idea that we can call our change in energy our work. And we have an equation in our data booklet that says that potential difference, or voltage, is equal to work over charge. So if this is true, then we could solve for work, which is what we're looking for, the gain in energy, right? Determine the gain in potential energy. That's our change in energy. That's our work. If we solve this equation for work, we can say, therefore, work is equal to a charge, right? Multiply both sides by Q, times a potential difference, right? A charge times a voltage. And we can substitute in some numbers here. We have a charge of 5 micro, that's times 10 to the negative 6 coulombs, times a potential difference. That's the difference between the potentials. If we go from positive 2 up to positive 18, that's a potential difference of 16 volts. And if you multiply this out, you're going to get 8 times 10 to the negative 5th joules, or 80 microjoules. All right. Well, problem number 2 is right here. Electron volt is a unit of what? Well, we've already seen here that a charge times a voltage gives us not a voltage, not a charge, but energy or work, right? So an electron volt, an electron is a charge times a volt, actually gives us energy. So an electron volt is a unit of energy. And it is equal to, well, let's take a look at what it's equal to. 1 electron volt is equal to 1 electron times 1 volt. All right. Very often, problems in IB will tell you that it's an electron and not give you the charge. But you need to be able to say, well, I know what the charge of an electron is. I have my data booklet with me at all times, and I can always look up the charge of an electron is an elementary charge right here. E, it's 1.6 times 10 to the negative 19 coulombs. And for an electron, it's a negative 1.6 times 10 to the negative 19 coulombs. For a proton, it's a positive. But, all right, so we know what the charge of an electron is. It is 1.6 times 10 to the negative 19 coulombs times 1 volt. And a coulomb times a volt is going to give us an energy unit, and that's the joule. So we're going to get a coulomb times a volt gives us a joule. And how many joules is this? Well, 1 electron volt is equal to 1 times this number. It's 1.6 times 10 to the negative 19 joules. All right? This is important. An electron volt is a unit of energy that is equal to 1.6 times 10 to the negative 19 joules. And a joule is a coulomb times a volt. Rock on. Next, let's talk about 5. 5 says this. It says, state the difference between PD and EMF. And let's talk about that. This has to do with a conversion of energy between two different types. One type is electrical energy, so one type is electrical energy. The other type is any other form of energy. All right. So in our problems, often we will have energy changing either from some other kind of energy into electrical energy. And if that's the case, if we are going this direction, if we are going from some other form like chemical energy into electrical energy, we are talking about an EMF. And if we are going from electrical energy into some other form, we are talking about a potential difference. So a light bulb, for example, takes electrical energy and converts it into light. That's taking electrical energy into some other form. And the voltage drop across an electric, if you measured the voltage across a light bulb, that would be called a potential difference. A battery, like the one in your car or the one in your cell phone, takes chemical energy and converts it into electrical energy. And if you measure the potential difference across that, if you measure the voltage across the battery, you would be measuring an EMF. All right. It's a little bit confusing maybe, but this is the gist of it, that a PD is the difference in potential from electrical to any other form, and an EMF is any form into electrical. All right. Number 7. 7 says this. It says, use the definition of potential difference, determine the PD between two charged surfaces if an electron's electric potential energy changes by this many joules as it moves from one surface to the other. All right, so let's say we have two charged plates. All right, I'm going to draw that. One plate has got a bunch of negative charge on it, and the other plate has got a bunch of positive charge on it. Let's say it's the same number. I think I'm a little off, but there would be an electric field between these two plates, right? And the electric field would stay constant anywhere between these two plates. And so we would draw the electric field lines maybe something like this. And here, if the plates ended, right, we might have some kind of a situation like this. And we would show the direction of the electric field with arrows that would show which direction would a positive charge go. And so if we put a positive charge here in the middle, it would want to run away from these positive charges and move towards these negative, right? So each one of these electric fields would have some direction. All right. Now if we plop our electron in here, and let's say we start our electron over here. So here's E minus, that's my electron. It's going to accelerate as it moves across the gap between these two plates, and it's going to gain energy. And the question that they've asked us to determine is, what would the potential difference be? What is the difference in voltage between these two plates if an electron gains this much energy as it moves from one to the other? And in order to solve that question, we need an equation that looks something like this. It's in your data book. It says this. It says that V, potential difference, is equal to work over charge. And that means this, that work is really our change in energy. And that charge, the charge, they don't give us a charge, but we know, since they are talking about an electron, we know that this is the charge of an electron. All right, so let's calculate this. Our change in energy, it tells us, is 3.45 times 10 to the negative 17 joules. And the charge of an electron we know is 1.6 times 10 to the negative 19 coulombs. Crunch that out, I get 215.625, but that is a lot. Volts. That is a lot of significant figures, right? And really, they only give us 1, 2, 3 significant figures. And the data book, when it gives us the elementary charge, gives us 1, 2, 3 significant figures. And so we should have 3 significant figures in our answer. That means we want to round off after 1, 2, 3 digits here. Because the next digit is a 6, we're going to round up. And I would represent this as 216 volts. Number 10. Number 10 says, find the power converted from electrical to internal thermal energy by a heating element. So if we're going from electrical into some other form like thermal energy, right, heat, this is a PD, a potential difference, all right, by a heating element that draws 2.6 amps of current when the potential difference across the element is 120 volts. So we need to manipulate some equations in order to get started here. I want to give you 2 equations that are in your data booklet, and we'll go from there. The first one says something along the lines of V is equal to W over Q, right? And we have another equation that says Q is equal to I times T. All right. And we know something else. We know that power is in watts. That's in joules per second. We know that power is equal to energy or work divided by time. All right, so we need to feed some of these things in. I'm going to say I want to replace this Q in this equation with this IT. All right? And I want to replace this W with what W is equal to here. And so let's solve for W there. So if power is equal to work over time, we can say therefore work is equal to power times time. So let's take this and feed it in for work in this equation. And rewrite my equation then that V, potential difference, is equal to, let's not write work, let's write power times time. And let's not write charge, let's write current times time. All right, and these 2 times are going to cancel out. And so I can write that voltage, potential difference, is equal to power divided by current. But my problem doesn't ask me to find potential difference. It says find the power. So find the power. So I'm going to solve this equation for power and write if voltage is equal to power over current, therefore power is equal to voltage times current. And they give me voltage, that's V, and they give me a current, that's I. And so I'm going to fill those things in. My voltage, my potential difference, is 120 volts. My current is 2.6 amps. And therefore I can solve for my power. My power is going to equal 120 times 2.6. Need my calculator because I haven't done it yet. $312. And the unit of power is the watt. So for number 10, you should get an answer of 312 watts. If you wanted to write significant figures, I think that they give you two significant figures in your current, so you probably write this as the power is then equal to 310 watts. Bravo for thinking of that. On an IB test, as long as you're within one significant figure of the correct number, then you are not going to be marked down for it. So this would not be marked down, but this is actually the best answer that you can give. All right? Okay, let me know if you have more questions with work. I love getting emails asking for specific things, and I try to help as much as I can. If you have questions about this video, let me know about that as well. All right, bye.